Hi, Assalamualaikum. Today, our group will be presenting on gas chromatography, also known as a GC, which is an important analytical technique used in chemistry. I will begin with the introduction and focusing on the background and the development of gas chromatography. Gas chromatography was developed in the early 1950s following the work of Chm Martin and Rlm Singh, who introduced the concept of partition chromatography. Building on this idea, Martin and James developed the first practical gas liquid chromatography in 1952. This allowed the separation of volatile compounds based on how they distribute between a gaseous mobile phase and a liquid stationary phase. Over the time, improvements such as capillary columns, temperature programming, and more sensitive detectors greatly increased the efficiency of gas chromatography, making it a key technique in the modern analytical chemistry. Gas chromatography, or GC, is an analytical technique used to separate, identify, and quantify volatile and semi-volatile organic compounds. It is widely applied in environmental analysis, pharmaceutical, food chemistry, and forensic science due to its high sensitivity, good resolution, and fast analysis time. GC works by separating compounds based on their distribution between a mobile gas phase and a stationary phase inside a column. The sample is vaporized and carried by an inert gas such as helium or nitrogen. Components separate according to their boiling point and polarity and elute at different retention time, which are used for identification and.
This slide shows the objective of this experiment. The first objective is to determine the retention time of n-butanol and 2-propanol. Second is to identify the component present in a standard mixture based on the retention time. Third is to identify the component present in an unknown sample. And lastly, to determine the effect of temperature on the retention time and peak resolution.
Next, we move to the methodology. Looking at the schematic diagram, we can follow the path of the sample step by step. First, we have the carrier gas supply, usually helium, nitrogen, or hydrogen. This gas acts as the mobile phase and continuously flows through the system. The carrier gas passes through the gas flow and pressure regulator, which is important because a stable flow rate ensures accurate and reproducible results. Next, the sample is introduced through the injection port. At this point, the injection port is maintained at a high temperature so the liquid sample instantly vaporizes. Once it vaporizes, the sample enters the GC column, which is located inside a temperature control oven. This is where the real separation happens. After separation, the compounds exit the column and reach the detector, specifically a flame ionization detector, or called as FID. Finally, the signal from the detector is sent to the computer, where the data is processed and displayed as a chromatogram. Moreover, we move to the name and function of each component of gas chromatograph. First, the carrier gas supply functions as the mobile phase, transporting the vaporized analytes through the column. Commonly used carrier gases include helium, nitrogen, and hydrogen. Second, the gas flow or pressure regulator controls the pressure and flow rate of the carrier gas entering the system. Precise regulation is essential to ensure consistent retention times and reproducible results. Third, the injection port, also known as the sample inlet, is used to introduce the sample into the GC system. It is maintained at an elevated temperature to ensure rapid vaporization of the sample. Fourth, the GC column is the primary site of separation. It contains a stationary phase that interacts differently with each component of the mixture, causing them to elute at different times. Then, the oven provides controlled thermal conditions for the column. Temperature programming is often applied to optimize separation efficiency and reduce analysis time. Next, the detector. specifically the flame ionization detector that detects organic compounds as they exit the column and converts their presence into an electrical signal proportional to their concentration. And finally, the computer and data analysis system records and processes the detector signals, displaying the results as a chromatogram for a qualitative and quantitative analysis. From this video, we can see that before the actual injection, the auto-sampler pricks the syringe into the vial several times. This step is done to clean and condition the syringe by removing any residue from previous samples, which helps prevent carryover. The syringe also draws and expels the sample into the waste vial to remove air bubbles and stabilize the injection volume. This ensures the syringe delivers an accurate and consistent amount of sample. Only after these steps the syringe draw the correct volume and inject it into the injection port, while any excess sample is discarded as waste. Overall, this process improves accuracy, precision, and reliability of the GC analysis. From this video, we can see that before the
Next, let's move on to the discussion. This slide shows the chromatogram for pure 2-propanol, and it was observed that the major peak is at 2.71 minutes with a total area of 99.98%, indicating that the sample was highly pure and well prepared. The short retention time can be explained by the low molecular weight and high volatility of 2-propanol. These properties cause the compound to spend less time interacting with the stationary phase, resulting in faster elution. A very small minor peak was observed at 3.6 to 9 minutes, which may be due to trace of impurities or background noise. For pure N-butanol, it is shown that the major peak is at 5.986 minutes with a total area of 99.73%, confirming the high purity of the sample. Compared to 2-propanol, N-butanol has higher molecular weight and lower volatility, which causes stronger interaction with the stationary phase. As a result, it remains in the column for a longer time and shows a longer retention time. Minor peaks observed at 2.651 minutes and 2.982 minutes, indicating small amount of impurities. Next, the slide shows the chromatogram of the standard mixture analyzed at 70 degrees Celsius. There were two main peaks observed, which is the first peak is at 2.677 minutes with a total area of 38.21%, which is corresponding to 2-propanol, and the second peak is at 5.834 minutes with a total area of 61.77%, which is corresponding to N-butanol. The identification of these peaks was done by comparing their retention times with those of the pure compounds. This confirms that both 2-propanol and N-butanol are present in the standard mixture. Next is standard mixture at 100 degrees Celsius, which shows a noticeable decrease in the retention time for both compounds. There were two peaks, which are 2.27 minutes with 38.32% area. This is 2-propanol, and another one is 3.285 minutes with 61.67% area, which is N-butanol. This decrease in retention time is due to increase analyte volatility at higher temperatures. However, the peak areas remain almost unchanged, indicating that the temperature does not significantly affect the relative composition of the mixture. Standard mixture at 140 degrees Celsius shows the retention times decreasing even further than 100 degrees Celsius. There were two peaks with 1.957 minutes with 38.31% area, which is 2-propanol, and another one is 2.243 minutes with 61.63% area, which is N-butanol. It is clearly shows that increasing temperature speeds up the elution process by reducing interactions between the analytes and the stationary phase. Despite the faster elution, the peak areas remain consistent, showing that quantitative results are not affected by temperature change. Next, we are going to identify unknown solution. This slide shows the chromatogram for the unknown solution, which has a major peak at 5.971 minutes with a total area of 99.739%, which closely matches the retention time of pure N-butanol. Minor peaks at 2.652 minutes and 2.933 minutes. These indicate traces of impurities. Based on the retention time comparison, the unknown sample was identified as N-butanol.
This slide shows the effect of column temperature in gas chromatography. Column temperature is a very important parameter because it directly affects how fast compounds travel through the column and how well they are separated. First, let's look at the increased column temperature. When the column temperature is increased, the analytes gain higher vapor pressure. Because of this, their interaction with the stationary phase become weaker. As a result, the compounds move faster through the columns. This causes the retention time to decrease, meaning the peaks elute earlier on the chromatogram. Next, for reduced column temperature, at lower temperatures, analytes have lower vapor pressure. This leads to stronger interaction with the stationary phase. The compounds then move more slowly through the column, which increases the retention time. Therefore, the peaks appear at longer times in the chromatogram. In conclusion, the objective of this experiment was successfully achieved, where the retention time of 2-propanol and N-butanol were determined using gas chromatography. Pure 2-propanol showed a major peak at 2.710 minutes with a total area of 99.98%, indicating high purity and a short retention time due to its low molecular weight and high volatility. N-butanol produced a major peak at 5.986 minutes with a total area of 99.73%, showing a longer retention time because of its higher molecular weight and lower volatility. The standard mixture contains both alcohol at 70 degrees Celsius, 2-propanol eluted at 2.677 minutes and N-butanol at 5.834 minutes. When the temperature was increased to 100 degrees Celsius, the retention time decreased to 2.274 minutes for 2-propanol and 3.285 minutes for N-butanol. At 140 degrees Celsius, further decrease were observed, with 2-propanol at 1.957 minutes and N-butanol at 2.243 minutes. The unknown sample showed a major peak at 5.97 minutes with a total area of 99.738%, which closely matched the retention time of N-butanol, confirming that the unknown is mainly N-butanol. Minor peaks at 2.652 minutes and 2.933 minutes, indicating the trace impurities.